Okay, so hello everyone, and welcome to the week 4 lecture. And this lecture is highly linked to the tutorial we're going to have this week. So I highly recommend it that you watch this lecture and try to learn about the practices we're going to have. Try to do some of them over the Sunday and come back to me on Tuesday with a knowledge. So the topic is going to be about the material selection basics. You'll see that this chart is going to be used very dense with very high density during this session. So we're going to have a look through it. First, the exploring of the material property charts. During the previous modules, we considered that some of the common properties accepted by the material, and we also considered that the given material will accept the property profile, and that is a certain mix of the property that act like a fingerprints of the material. So considering that the property profile of the candidate materials is going to be critical for making the good material selection, the challenge is going to be in the finding of the relevant information of the data. The subsequent exercise in the comparison and the contracts for different materials is an additional difficulty. This challenge was recognized by Professor Michael Ashby, whose work has led to the development of the Ashby plot charts, which is form of the basis for the Granta CES EduPack, and some of these charts will be presented as an example in this lecture. So consider a scenario where a high stiffness is going to be required for a given application. An example would be for a cantilever beam supported on one end only, and it must resist a deflection under the load. Hence, a relevant material property is a Young modulus. As per below, you may find a symbol bar chart that's going to converse between the Young modulus for the range of different materials. Could the material selection be made now? And what do you observe from the plot like this? So technically, let's have a look before again to go to the answer. We can see that we have the Young modulus for four different categories of the materials that we have in general. Just give me 1 second. Okay, so the metals, the polymers, ceramics, and the hybrid. And you can see mainly that for the metals, we are going to have a higher value for the Young modulus. And this will be dropped for the case of the polymers, and it's going to be higher in the case of the ceramics, and it's going to be within the range in between for the case of the hybrid. In general, as you mentioned earlier, so you can find that the Young modulus range is going to be within span over 6 times the orders of the magnitude across the chart, and also the Young modulus for the polymers span 5 times orders of the magnitude. So that's the polymer. You can see that out of the 6, there's 1, 2, 3, 4, 5, 6. Oh, sorry, start from here. 1, 2, 3, 4, 5, 6. So the polymers is span over 5 of those 6. Also, you have that the ceramic and the metals are very similar in terms of the Young modulus, but what about the other properties that beyond the Young modulus? So that's the metals is going in these two spans. This is the same thing here. Some materials can span only for half times the orders themselves. Okay. So that's what we learned from this diagram, and this is a basic and a very simple basic analysis that we can talk about. So in the previous example, we just got the Young modulus. Now, what if the scenario was expanded to include an additional property such as the density? So the application might be looking for a lightweight components with a high stiffness. An example for that could be the connecting rod in the internal combustion engine, and our plot then can simply become one of the Young modulus with the density. So we added the density in the x-axis now. So you can once again need to know what we are finding here. First, that's the density below, and that's the Young modulus. These lines represent the value of the division of the Young modulus by the density value. So we divide that to a longitudinal wave speed, and we're going to check actually what we have. So if I get to look at the top corner here, I can find the ceramic is going to have the highest range for the Young modulus and the density at the same time. The same thing was going to be for the metal. It's going to be more density but less Young modulus value than the ceramic. The composite is sitting somewhere in between, and the polymers is sitting in between here with less modulus of elasticity, less value for the density. The foams actually expanded for a very long range, starting from here, for example, 12 up to, sorry, that's 15 up to 100, and that's 300, 400. So a span for long term. So what we can observe in this one can be simply summarized on the next page. So the property range from bubbles to or regions according to the material family, as we can see here. Second, that we can notice also that there is no material exists that combines the high E with the low rho. Okay, you can see that even the foam have a low rho, low E. There's nothing with the high E or the high modulus of elasticity and low density, nothing in this area. There's a tendency for the E to increase with the increased value for the density. Some of the families have a larger range in one property or the other. Okay, so this one have a larger range in both. Okay, foams tends to span in both the density and the Young modulus. Well, this one, for example, the composite is going to be very low extent, very low range in the case of the density, but acceptable range in the case of the Young modulus. So as noted, the plotting of the two properties together typically will lead to the region of the similarity that represent the material families. Whilst these were going to be explored earlier, they are revisited here to aid in the development of the familiarity. So these are the families, the metals, ceramics, the ceramics composite, non-technical ceramics, and the polymers. And here the classes of each one of the family members and their short names. You can use that actually to make your research later. So the below table from the HBA can correspond to the material families and the classes that are contained within. Okay, so this is extension of this table. We can go to the isomers, the hybrids, which are the composites, the hybrids, which are the foam, and the natural materials hybrid. Now, adding the material classes to our plot of the Young modulus and the density will provide a finer details and aids in the identification of the actual material for selections. Additional detail can also be included, such as the longitudinal wave speed or the relationship between the E and the rho, which reflect the loading scenarios. So here what we are going to notice by this stage, by the way, this is something that you need to do in the quiz. I mean, putting the include the other details like the names of the classes, the wave speed, the relationship between the E and the rho. So what we are going to notice right here is going to be the following. First, some of the classes, especially the are especially narrow in their range of the properties, and other are going to be very wide. Now the same thing we can see here. If I can talk about the forms, it's going to have a wide range in both density and the E. Those are going to be narrow, and so on. No material exists in the that combines the high E and the low density, and there's tendency for the E to increase with the increased rho value, and some families has larger range in one property or the other, but forms tend to span to both. So strength is another material property that is often going to be relevant to the design application. However, the strength is highly variable and it depends on the mood of the failure as well as the processing applied to the material. So for the metals and the composite, the strength refers to the tensile strength at the failure. For the ceramic and the glasses, it refers to the compressive strength at the failure. And for the polymers or the elastomers, the strength refers to the tensile tear strength. The strength with the density as a useful material property chart. So what do we notice in this chart here? Once again, we can see that the tendency of the elongation in the strength variable, and also the diamond has the highest value for the strength over the density ratio. And that's what we can get here. Once again, you just need to locate the diamond on this chart, and many diamonds going to be within the ceramic. That's the ceramic. The diamond is going to be sitting at the top there, have the highest value for the ratio between the highest density and the the highest strength and the density. So you will find actually that because when we come to this stage, for example, for the tungsten alloy, for the metals, you will find that the value for the strength maybe is going to be dropped down to 900, and the density will be increased to 11,000, while in the case of the diamond is going to be about 3,000 against the density of 3,000. So this will make it as 1. So let's have a practical question, which is why the steel is going to be used for the springs in some cases and the rubber used in the others. So you can see once again that we have the new chart, which is about the Young modulus against the strength, because we want to have some elasticity in the case of the spring, of course. So consider the chart of the Young modulus with strength, which includes yield strain value, which is the strength over the modulus of elasticity, contours as you can see in these lines. Okay, so we're going to make these lines for the contour, and this plot will relate the material stiffness to the strength, and the yield strain indicate the measures for the elongation and the yield stress or the fracture. So what do we notice here? Again, we're going to notice that the ceramics will tend to have a very low yield strain. Also, the metals, composites, and some of the natural materials have a slightly larger yield strain value. Okay, now let's check that. Ceramics. Well, the ceramic is the top one. That's the technical ceramics, and the diamond is one of it. It's going to have very low yield strain value. And then we are going to go for the metals and the composites, which is going to be here, the purple one, and it's going to have a slightly larger yield strain value. And then we come to the polymers. Okay, that's the polymers, and the foams will accept a broader range of yield strain, but extend beyond the value of the metals, which is 1 in 1,000 up to 1/10. And the elastomers at the end is going to, actually we talk about the elastomers here, okay, which is going to accept the highest yield strain value of 0.1 to 10. Okay, so from 0.1 up to 10 is for the elastomers material we have here. Now we go for the relating a material property to the density is useful when the material mass is going to be important. For example, where the component needs to move or carried. Such a property are going to be identified as a specific value. For example, you can have the specific modulus and the specific strength. Specific modulus is going to be the modulus of elasticity divided by the density, and the specific strength is going to be strength divided by the density. So you can see in this diagram, we're going to have the specific modulus against the specific strength. Again, what we can check for this one, that's the ceramic, that's the composites, that's the metal, and that will be the polymers, and that will be the foam, and that will be the elastomers. So what we can see in this one, okay, this modulus. This specific strength chart is useful for designs that consider stiffness and strength at the minimal weight. In other words, the mechanical efficiency. So what did we notice here? First, we need to know that the ceramic will dominate the upper right region. The upper right region is going to be for the ceramic, but the brittle failure must be considered for the ceramic. The composites now are going to be also in the upper right region. The metals here in the purple one are going to be the central on the chart due to their high density. The polymers are also going to be the central due to that's green one. Okay, sorry, that's a blue one. It's going to be at the center due to their very low density. The elastomers and the foams are going to be in the lower left and the lower central region of the chart. So now we can ask a question: what could be a good material for the mountain bike frame? Definitely ceramic is not going to be the one. The foam is not going to be the one. So we're looking for something within that range. So selecting material based on the strength may lead to the catastrophic failure if the material is not going to be able to plastically deformed, or for example, it's going to be a brittle. So we can simply, the brittle failure will occur rapidly and is going to be initiated by the presence of the cracks or the defects. And fracture toughness is going to be the measure of the material's resistance to the crack propagation. Below is a fracture toughness with Young modulus chart. So that's fracture toughness, that's Young modulus. So once again, the highest value for the fracture toughness means the material is going to be more resistance to the crack propagations. And once again, that means it's going to be more able to be plastically deformed. So now that's the multiple value for the K1 square multiplied by divided by the E value. We're going to have these lines to be calculated. Actually, don't have calculated, just make it using the filter we have on the software. Okay, so included in this chart is going to be the toughness, GC, and this is going to be a measure of the ability of the materials to absorb the energy. So comparing the polymers and to the ceramic, the K1C value are going to be similar, which will suggest that the two material families are going to be equally brittle, which is not true, because when the GC is going to be included, the polymers have a value of about 10 kilojoule per square meter, while the ceramic is going to have only 0.121 kilojoule per meter square. Okay, hence the polymers can absorb something like 10 to 1000 times more energy during the crack propagation. So the fracture toughness with strength is also a very useful parameter to be select the material. So as seen below, there's a tendency for the fracture toughness to increase with the strength, which is going to be intuitive. So this relates to the ability of the material to resist the crack propagation, which fundamentally relates to the yield stress. So from this chart, it can be seen that the materials that heal before the fracture are going to be at the top right. For example, is going to be for the metal. So once again, the materials that are going to be healed before is going to be fractured like that, which have higher plasticity, like the metals, will be sitting at the yield before the fracture is going to be sitting at the top right. The materials that fracture before yielding, which is going to be more brittle, have high elasticity but no plasticity, are going to be located at the bottom left. And we have another feature is going to be the exclusion of the triangle in the bottom right region. And this results when the dimensions of the crack tip is going to be less than the atomic size. Now, the material property chart are also available for the properties other than the mechanical. For example, I can have thermal conductivity with electrical resistivity. So we talked about those two parameters. Thermal conductivity relates to the transport of the heat, electrons and the photons. And the electrical resistivity related to the transport of the electrical charge carriers, like the electrons and the ions. So what do we notice in this chart between the electrical resistivity against the thermal conductivity? First, for thermal conductivity, the range is going to be 5 times the orders, whereas the resistivity range is going to be 28 times the order. So 10 up to power 1 up to 10 up to 28. And this is starting from 0.01 up to 1000. So this is 5 times the power of 10, and this is 28 times the power of 10. The ceramic dominates the upper right region. It's here, okay? And the question is why. Now that means that the ceramic is going to have a quite low thermal high thermal conductivity, was going to have low electrical conductivity. That means it's going to have higher resistivity, because you know resistivity is 1 over the conductivity or the electricity. So basically, let's think here. Still, we said that we can have some of the ceramic type that can do some electrical conductivity. Also, we can see that the metal will show a linear correlation here. It's a linear correlation between the thermal conductivity and the electrical resistivity. Now, I would like to answer why. The foams here, okay, the foams and the technical ceramics share the similar resistivity, but vastly different in the thermal conductivity. Okay, so for the resistivity, thermal resistivity is going to be the same, but for the thermal conductivity is going to be quite different. Now, when we say why, because it's one of their properties. We said that the difference between that is going to be the electrons and the phonons against the performance of the electrons and the ions. Now, consider the thermal expansion versus thermal conductivity. You can see that thermal expansion relates mainly to the displacement of the atoms as the temperature is going to be changed. We said that some material is going to be expanded in size when we're going to have heat to it. Thermal conductivity is able to transfer the heat through the material. So stemming from the bonding characteristics, as you can see here, what do we notice in this one? Now you can see that this one is different from the previous one because we took in thermal conductivity against the thermal expansion. You can tell that the good thermal conductivity material seems to have a less thermal expansion, and vice versa for most of the types. So the polymers and the elastomers and the foams that we said have a lower thermal conductivity, as you can see here, okay, which used as like an insulators, is going to have a higher thermal expansion. So apart from the metals, increased thermal expansion correlates with the reduced thermal conductivity. Also, the polymers tends to have the highest value for the alpha. And also, many materials types can have a low value for the alpha. The alpha is, of course, the thermal expansion. Diamond has the highest value for the lambda, or higher value for thermal conductivity, but have a low value for the alpha. Now, I would like to get me an answer for why that's happened. So you can see it. The diamond is sitting here at the end. Very good thermal conductivity, but very low thermal expansion. Now, why the lambda over alpha is an important design consideration? So let's go for the other parameter, which is going to be the expense. Expense is another material property that's often going to be a design consideration. However, it's driven by many factors. So we can consider either the price per unit weight, which is the most material classes range between $1 per kilograms up to $100 per kilograms in USD at the time of writing this document. When considered as a relative weight, the polymers compare close to the metals, but the volume considered will be much higher due to the differences in the density. Hence, the price per unit volume needs to be considered in parallel. So you can see these two different diagrams, okay? And from that, you can see from the first one, the metals, the polymers, the ceramics, and the hybrid. The price per unit weight is going to look the same, actually, with the same pattern with this one, but this will tell you that the price value is going to be different. Now, why the silvers and most of the metal will remain at higher price per unit volume compared to the uh, polymers? Because once again, their density is higher. That means their volume, for the same volume, 1 cubic meter of steel, for example, is going to have something like 7,300 kilograms, while the mass of the same size of the polymers maybe is going to be anything between 300 to 800 kilograms, depending on density. Of course, I don't remember the density of everything. So when the density is going to be lower, the volume tend to be lighter. A factor with a growing importance is going to be the embodied energy, or the HP, and this is the measure of the expended energy required to produce the material, and reflects the associated emission value for the carbon dioxide, carbon monoxide, and the carbon hydroxide. Um, for example, what we mean by the greenhouse gases. So, as with the cost, the embodied energy should be considered as a unit mass and a unit volume basis as well. So, this is the value for the energy, and this is different parameters. That will be the cost per unit mass, how much per kilogram, and this will be the cost per unit volume. Now, this module summary was: the material selection is based upon the design consideration involving the specific material properties, and the material properties charts enable us to compare between the materials according to the selected properties and assist with the selection decision. So identifying the patent properties at the outset is critical to the selection process and will be explored in the future. You must become familiar with the Granta CEC EduPack, EduPack software, and actually you should practice on everything we've done today, because this will be a part of your quiz for the next week. Okay, so thank you very much, and we're going to meet you in the class very soon.